We are seeing you now.
You are? Okay, good. Thank you. I'd just like to introduce our speaker this morning. I've sent out everyone an important page describing Dr. Hargraves' background as a study leader for energy policy at Dartmouth, ILEAD, Chief Information Officer at Boston Scientific Corporation, and a senior consultant with Arthur D. Little. And he founded a software firm at Dartmouth College, where he's assistant professor of mathematics, or was, and associate director of the Computation Center. What I wanted to do is read to you from the back of the book this morning, a good paragraph. He says, "Energy cheaper than coal will dissuade all nations from burning coal." That's a powerful statement, and I think there's a lot of truth to it, particularly in the new coming nations that Dr. Hargraves will be talking about. Innovative thorium energy uses economic persuasion to end the pollution, to provide energy and prosperity to impoverished peoples, and to create energy security for all people for all time. It's a very powerful statement, but I think a lot of reality in that statement. And so I'm delighted to have an old acquaintance and a new friend, in a way, Dr. Robert Hargraves. Dr. Hargraves, we're delighted to have you with us this morning, and you have the floor.
Thank you very much. Since I wrote the book, I also joined a company, and I'm a co-founder of Thorcon International, where we're actually trying to accomplish the things that you mentioned from the back cover of the book. I've prepared about 60 slides or so today that we'll ask through our talk, and we'll have a discussion at the end. But during the talk, please feel free to stop, and we can spend a minute or so on answering questions that come up as they come up, but we can't spend 15 minutes, so we won't have time to do them all. Give me just a second to get this going. And open. Okay. And it says it's preparing the slides. So we have just a second while my computer continues. There we go. And I will let me maximize this darn thing so I can see. And you should be able to see and tell me if why can't I do that?
I see the slides fine, Robert.
Okay, good. And you see me too in the lower right.
Yes, as well as
Okay,
over
great.
on the far right. So I see you twice.
Well, there you go, everybody. Okay, so we're going to talk about 4 topics in today's meeting. First, we're going to talk about the need for energy and what it does for people. Then we'll talk about Indonesia, because Richard Steve asked specifically, why Indonesia? And I'll try and answer that question for you. Then we'll talk about the liquid fission reactor that Thorcon is designing. And then we'll talk a little bit more about trying to deal with reducing CO2 emissions by electrifying our world with ample electric power. So wrong button. First, I want to just be sort of critical about politicians. This is a graph of CO2 emissions measured at that volcano on an island in Hawaii, and they go up and up and up. And here are all the efforts of political bodies that are spending a lot of money trying to solve this problem. And we have yet another meeting, the COP26, coming up shortly. We're going to try again. But I think just looking at the gross picture of what politicians do versus what burning fossil fuels does, it's clear to me that there's no hope that the politicians are going to come up with anything that's effective. So our take on fixing the climate is totally different. First thing to notice is that there are 1 billion people in the world almost who have no access to electricity at all. let alone worrying about climate change. Moreover, there are 3 billion people who have only a few watts of electricity available to them. About 3 billion people don't have enough electricity to run a refrigerator. We also have the problem about thermal energy for indoor use for cooking. In India, women use dung and firewood to cook, creating particulate hazards in their homes. They also have a lot of labor to do to prepare the meals this way, to go out, try to fetch firewood and really denude the forests of wood. So it's a problem that can be solved with better energy. If we can solve that problem, it gives women some time off. They don't have to run to the riverbank to do the laundry. They have time to perhaps read, to perhaps study, to be educated, to be eligible to get jobs, to get money, to become independent, and to make their own decisions about bearing children. And we find that in those areas where women are more educated and free and independent, the birth rate drops. So, for example, in this graph, which is also in the book, each dot represents a country. And in the horizontal axis, the number of children born per woman. And in the upper or vertical axis, the GDP per person, which is very closely related to income per person. Now, I drew a red line for the stable raw birth rate, the stable replacement rate, a little over 2 children per woman. If we're below that rate of reproduction of humans, then we can stop worrying about overpopulating the planet voluntarily. So you see clearly that the people in wealthier countries have lower birth rates. And I just sort of arbitrarily wrote the green line across there at about $7,500 per year to indicate prosperity. And those countries that are not prosperous have many more children per woman, and their population rises. Here's a similar kind of graph. This one is in the horizontal axis, the GDP per capita. Each dot represents a country, as in the previous graph. And in the vertical axis is power consumption in terms of kilowatt hours per year. So again, the least populous, least prosperous countries are in the lower left. And there is a relationship that looks pretty clear that as you increase electric power, which is a very valuable kind of energy to have because it provides motive force, it provides lighting, it provides heat, transportation, and so on, that GDP per capita rises. This is well known to the developing countries. The slope of that curve is $32 billion of increased GDP, gross domestic product, per 1 gigawatt capable electric power plant. That's a good return. It's a good return. The plant might cost $1 billion once, it has operating costs, but it adds or permits the addition of $32 billion of GDP. It doesn't cause it, of course. You need good government, you need roads, and so on in order to have GDP rise, but it is an essential to add the capability for prosperity for people. Here's global electricity use today. Let's look at the red bar on the left. The height of that bar, it represents the electric power consumption in the US in average watts. In North America, it's about 1,500. For the US, it's about 1,200, I think. The horizontal distance is the number of people in that geographic area. So the area of that red bar, 528 gigawatts, is the total amount of average electric power consumed by people in North America. You see the EU at about 700 watts average power consumption. Remember, this is 24 hours a day, 365 days a year average. China reaches its level of prosperity at about 400 watts average. But the rest of the world has a long way to go. Global electricity use today is about 3,000 gigawatts average. We need power plants that are more capable than that because they don't run all the time, of course. But that's the average use worldwide. So the whole yellow area is the growth potential. That says that if those regions were to become as prosperous as North America, we'd have what, 1,500 watts times 8 billion people or so. You know, we'd be up in tens or twelves of gigawatts, thousands of gigawatts. So what do the developing nations do? The answer is they build coal-fired power plants. China last year did about 40 gigawatts of coal-fired power plants. India has about 37 gigawatts of coal-fired power plants under construction now, and another 30 gigawatts of coal-powered plants in the development stage. So here in the US, we somehow think coal is obsolete, but to the developing world, this is a way to generate energy that's relatively inexpensive. It's a tried and true technology. It operates 24/7. It's the kind of power that's needed to grow industries, to grow commerce, and so on, data centers. So they are building them. In the website of our company, which is thorconpower.com, I know there's a set of references there to the work that was done by Greenpeace and Coalswarm and so other, that lists every coal. It's a spreadsheet. It lists all the various coal-fired power plants that are being built today. And there may be 600 gigawatts of them being planned. So they want it because it brings to them the prospect of prosperity through using electric energy. Suddenly, I'm going to talk just for one slide here about renewables. We have a big movement worldwide to say we want renewable energy, but I call it the 100% delusion. People think we can do this and provide 100% of our power that way. But they don't seem to notice the obvious thing. The sun sets and the wind lulls. What are you going to do to provide power during that time? Some people say, well, perhaps if it's the wind is lulled in New Hampshire, it'll be windy in Vermont, and we can get Vermont power and so on. But weather patterns are half a continent wide. There's a lot of correlation. We can have wind lulls that last a week or longer. And the other answer is, if you read Bloomberg New Energy and you read Lazard's analyses, is, well, we've got batteries. The cost of lithium-ion batteries is dropping rapidly. It's exponential. But let's do the math for a second. If we wanted to have stored just one day, let alone a week, if you wanted to store just one day of world energy, and we had to do that worldwide, near every power plant or every use of electricity, that would require 36 billion Tesla power walls. That would require building 1,000 of them per second for 10 years. This is an unimaginable effort. It would cost $250 trillion just for the list price of the batteries plus installation. This is not a feasible thing to do. It is the delusion. Everyone thinks this is going to happen. The National Renewable Energy Laboratories give grants to college faculty members and so on. We have zillions of papers published by guys like Jacobson and so on that try to say, oh, we can do that. Yes, we can do that. But if we just look and think at the fact that the sun sets and the wind lulls and batteries are too expensive, you can think for yourself and say, this is impossible. We read in the newspapers every day about new ways to do it. Heavy trains that go up mountains to store energy. And then when we let the heavy train roll down the mountain to retrieve it. But any kid who's taken high school physics should be able to do the math to figure out how much energy is stored that way and how much we actually use. It's not feasible. Anyway, that's the end of my rant on sun and wind. What about fission power? Well, they now choose 24/7 coal power. They want 24/7 energy, and they will choose fission power if it's cheaper. They're not so hung up on it as we are in the United States. Here's the economics that we have redone time after time in our design for the Thorcon power plants. That the capital cost in terms of dollars per watt of generating capacity for these liquid fission power plants is about $1.2. And a coal plant is more expensive. The cost is going to depend upon how much pollution equipment, scrubbers, and so on you put on it. But this doesn't count carbon capture or anything like that. The fuel cost, again, for fission is less than for coal because radium is so energy dense. And I have to get out of the way for you here. Whoops. I have to get out of the way and say that, there we are. The cost for coal-fired electricity is going to be about 5 cents a kilowatt hour. But from our liquid fission power plant, 3 cents. Those are persuasive numbers. If you're a developing nation, you don't want to have that much capital invested, and you want cheap electricity to drive your industries and commerce.
Could I make a comment?
Please.
I totally approve of this table comparing with coal, but wanted you also to mention that with regard to renewable energy, that those renewable sources generally last for 20 to 25 years, sometimes even less. I think some of the wind turbines offshore might even last only 10 to 15 years, whereas nuclear plants last at least 80 and perhaps longer. So you don't have to have that enormous cost that they associate with nuclear repeated every 20 years. It's a long-lasting investment.
Right. There are other fossil fuels. In the United States, we have a very inexpensive source of natural gas from fracking. And that's hard to compete with. But we can barely compete with natural gas power costs. In the developing world, where we have LNG tankers, don't forget that the compression, liquefaction, and transport of liquefied natural gas adds about 2 cents a kilowatt hour to the cost of LNG. In this slide, I'm trying to keep it simple and just deal with coal.
Sure.
Because coal is the biggest source in the developing world. We'll talk a little bit about what Thorcon is doing because I'm a co-founder of Thorcon. Here's just a couple of photos. Well, photos, they're actually from HB SolidWorks, which we use for designing the power plant. This is the real design. It's not an artist's rendition. They can build 33,000 gigawatts worth of power plants in a 30-year period. That is the existing large shipyards in South Korea, in Japan, and so on, have very high capacity to build fleets of steel vessels because all of world commerce takes place on them. So they have that kind of capability. 3,000 is the number I mentioned before. That's about the total amount of electric power now consumed in the world. So in a 30-year period, the existing shipyards could do the construction of power plants, again, that would be 24/7, no CO2, and cheaper than coal. Here's the shipyard that we expect to be using. This is Daewoo Shipbuilding and Marine Engineering, DSME, one of the three largest shipyard or shipbuilding companies in South Korea. This is a very competitive business. They have automated much of their capabilities to cut and bend and fabricate steel, and they're capable of fabricating many ships or many Thorcon hulls. The Thorcon power plant is designed to be a hull, to be built in a shipyard, to be then transported to its site. So for example, here it's not really a Thorcon ship, but after it's built in the shipyard, our intent is to tow that ship hull across the ocean and settle it in its destination. The first one we expect to be located and tested is here in Indonesia. We expect it to be, can you see my cursor? I don't know. I guess.
Not yet.
Okay, well, never mind. Above the J in Jakarta, you'll see a bunch of islands. In that area somewhere, we expect to build the pilot prototype, if you will, power plant. So that's where it will be. Now, Richard wants to know why Indonesia? And so I put together a few slides talking a little bit about why we went to Indonesia. We do that because Indonesia wants the electricity. In the United States, we have enough electricity. We went to the NRC. We went to the Department of Energy 5 or 6 years ago, and we told them of our plans to build a prototype plant, perhaps in the Washington State area, in the Richmond area. And we were basically rebuffed. They said, you have to follow all the existing rules for light water power plants that we have now. And it was going to cost over $1 billion to get the NRC to make a ruling as to whether we could do that. So since we were a startup company, we started looking elsewhere, and we finally found Indonesia. Indonesia is the 4th largest country in the world in terms of population. And we started making calls. The point here is they need the electric power. Point 2, the demand for mid-century is 350 gigawatts of electric power consumption. That's the demand that they want. Point 3, again, they want to grow by about all the way up to about 420 of capacity appropriate to their population. Point 4, we've mentioned before that they do want to grow the national economy, not just for GDP, but to provide more employment for the people. 4th most populous country after the US, after India, after China. And the leadership does not want to repeat the mistake of being so dependent on one source of energy, fossil fuel from coal. The leadership of Indonesia, again, we mentioned they're highly motivated to increase that generation capacity. And they are receptive to the new technology that offsets that offers low-cost, reliable energy. They're open to nuclear. They have research reactors, TRIGA reactors at some of the universities for R&D. They have also, I believe, a medical isotope generation business in Indonesia. So they do have a nuclear regulator already in place. So they're attracted to Thorcon because it's a scalable technology in the sense that we can build a power plant in a few years, and it's about a 500 megawatt unit that's towed in, and it's scalable in the sense that you can buy more units at about 500 megawatts each. So they're attracted to that aspect rather than very, very large plants. We have been working with potential suppliers for many years. As we evolve the design, we ask suppliers to give us some information, some estimates of costs and so on, and how long it would take to build things. We mentioned DSME, Daewoo Shipbuilding and Marine Engineering. Another supplier is Doosan Heavy Industries, which is an expert in steam turbines and generators and so on. So we expect that DSME will be the engineering, purchasing, and construction contractor, the main integrating company that will assemble the complete power plant in a hull, in one of its shipyards. Now, our design is meant to fit in the slips of these large shipyards. So we're being very specific about trying to develop power plants that can be mass produced by existing factories. The Indonesians reported again that the supply chain was established and had competent leadership. So the presidential office is supporting progress. They haven't endorsed everything at that point, but they support what's happening with Indonesia's exploration of deals with Thorcon. In fall of 2018, we did sign an agreement with the Ministry of Energy to study the demo plant. So we shared all our design work with them. Their research arm of the Department of Energy, P3 Tech, did a 12-month study, and the power plant utility, PLN, which is the company that distributes electricity throughout the country, and the nuclear regulator, Bapeten, also participated in this study. And in the end of 2019, the Ministry of Energy had a press conference to announce the positive results of the study and recommended that the government approve the program. There are many steps to go on. Remember, this is a democracy. It has many departments. And so we continue our work with the government to progress the permissions and licenses and permits and so on that are needed in order to put the prototype power plant there. The results of that were that we've signed memoranda of understandings with the utility company and the power company that the utility company owns, which actually operates power plants in Indonesia. They want that power plant, and we're discussing that our investors will own it and operate it, and there will be a power purchase agreement for 30 years at a price to be negotiated that's cheaper than what they're paying for electricity now, but is profitable enough to keep our heads above water. Indonesia's shipyard, PT PAL, is very interested in manufacturing the can. We'll talk about the way the power plant works. The can is a replaceable part that lasts about 4 years. And so there's going to be a need to continually remanufacture the can that contains the reactor per se. The governor of Bangka wants the demo plant in the Bangka Belitung province. In mid-year, we got, again, another green light to proceed with the Thorcon 500 megawatt demonstration plant, and the coordinating ministry for maritime and investment affairs sent us a letter supporting the demonstration program, and has also been appointed to take the lead in orchestrating all the other agencies that are going to be involved in the country's first nuclear power plant. Obviously, as a nation, they're not going to make a deal with Thorcon. They're going to make a deal to get a nuclear power plant and invite other such vendors to participate as well. But we have been working so closely with them for so long, and they're building confidence in what we're doing, and they like the idea of being in a leadership position and getting inexpensive electricity. So we continue our work to keep marketing and coordinating with Indonesia. Just this year, the governor of Bangka Belitung province sent a video address to a dinner that Thorcon had put together in Indonesia with the coordinating minister of maritime, the minister of energy, so on. This is all in the time of COVID, of course. So some of these people attend remotely, some are in person. PLN Engineering, remember PLN is the utility company. They're going to do a site feasibility study. There are 3 sites that have been proposed so far in the general area that I mentioned earlier. They'll do a grid integration study and a summary feasibility study. Again, yet another study. ITB, which is a respected university in Indonesia, has agreed to have a Thorcon research lab on the campus. We're going to do some of the molten salt testing. We have more salt properties tests we want to run. The molten salt, of course, contains beryllium. It contains thorium. It contains uranium. And there's a lot less red tape doing it in Indonesia than there is to try to do that in some of the US universities that we have been working with. 2 other universities in Indonesia are right now conducting a public opinion poll of about 1,500 people who are residents in that province, trying to understand how people will react to having such a power plant on a small island north of Java. So that's the status we have today in terms of the relationships with the Indonesian government. The other point is that we have an efficient nuclear regulator, we hope, Bapeten. Again, I mentioned before that they've had experience in nuclear power with the trigger reactors in universities and with medical isotopes being produced. In the US, we have the Nuclear Regulatory Commission. And I will point out again that the NRC can be very expensive and can be delaying. The NRC has not approved, let me put it another way, there's not been a new nuclear power plant designed and built in the US since the NRC was founded in 1975. All the power plants we have today predate the NRC. So they're in no hurry to approve new technologies in the United States. Bafokeng is willing to write.
What about the one in Georgia? Wasn't that approved by the NRC?
Yes, it has been. It's not running yet. Okay.
Okay.
And
but later this year.
Another
maybe.
exception is
Okay.
there is one that was put into operation about 5 years ago by TVA, but it was designed before the NRC was created.
So your point's well taken.
Grandfather. Anyway, so but Bafokeng is open because of point two, the government wants this kind of power. So the regulator is going to be open and cooperative. There's no pressure on the NRC to approve nuclear power plants today because the government really doesn't want them. Again, Bafokeng is agreeable to restricting oversight to just the things that are related to the safety of radioactive materials somehow being accidentally dispersed into the environment. So they're willing to restrict their work to just the things that are safety related. In the US nuclear power plants, for example, the NRC is very concerned about things like the steam turbine and so on, which are vaguely related to safety, but we're going to reduce the scope, and they don't want to reduce the scope of the work that they have to conduct. And that's going to work, we think, well. They're also agreeable to our plan, and that is to do step-by-step testing. In the vernacular of the nuclear industry today, what's in vogue is probabilistic risk analysis, where you create a model of the power plant and you create a failure probability for each and every component, and you basically multiply them all together and figure out what is the chance of releasing radioactive materials to the environment. And the answer is, it's a computer exercise, basically. And we've seen numbers that are something like in new designs, it'll be only once every 100,000 reactor years or once every 1,000,000 reactor years and so on. But the opponents of nuclear power, like Union of Concerned Scientists, point out that the history of nuclear power is not that way. There are accidents. And the realistic answer is maybe once every 10,000 reactor years. So the response of the NRC, the regulator, and the industry has been, oh, it'll never happen again, which is a wrong response. We have to be more realistic about what might happen. And we believe that we will demonstrate the various safety features of the power plant. I mean, in the US, we have many radiation barriers, but we would never disable one and try and test to see if the others work. Our intent is to do step-by-step testing of the demo plant and to illustrate to the regulator and others who are interested the proper functioning of all the safety features of the plant. We want to do what we call deterministic illustrations or deterministic proof to show the people in the regulator how the power plant works in upset conditions. We're also assured they will not delay our 4-year plan, but we have our own issues to deal with, and we are doing them now. We just recently raised more money from an investor, so that's accelerating our progress. We like that. Again, in summary, why Indonesia? Again, because the leadership is motivated. 2, the key agencies are on board with the project, and 3, under the direction or leadership or guidance of the coordinating ministry, which is run by a person who might be the number 3 powerful person in Indonesia. We also have a buyer of the power. PLN wants cheap electricity, and we're in the process of negotiating the power purchase agreement. Bapeten is promising to provide efficient regulation without untoward delays. Generally, time will tell. I mean, there are lots of agencies, there are lots of people who are interested in this project. And so we're pursuing our path because we think that this is the way that we can work to solve the world's problem. Energy cheaper than coal, built in shipyards in mass production that can be hauled other places in the world.
Could I ask,
Please.
possibly add a little question there? If you are successful in Indonesia and establish a track record there, you will have done so in an area that's more fraught with earthquakes and tsunamis than probably any other part on the planet. So that's another point that to consider, that you've picked an area that's seismically dangerous, and you're still willing to do that and feel confident in that. And that's an interesting point.
We'll cover that in a few slides. We're going to go a little bit into the technology in the next few slides here.
Okay, sure.
First of all, here's again a picture of the power plant. We won't cover everything in this presentation right now, but I just want to let you know that we have a complete power plant design. I'm standing in front of a label that says where the cans are. The cans are in those blue walls there, and the cans are the reactor per se, and they are replaceable. On the far right is a cooling pond that is used for the passive cooling systems that we have. On the far right, places to store used fuel and so on. The rest of the power plant is all the power conversion. Power conversion is the most expensive part of any power plant. And we use steam. We use a technology that's been refined for hundreds of years. That is the most efficient way we know how to convert heat into electric power. So it's all fit together in this 3D design. Just a little quick review of nuclear power. The way it works is a uranium-235 atom absorbs a neutron, becomes unstable as a U-236 uranium atom, and falls apart, in this example, to 2 fission products, krypton and barium, and releases 3 more neutrons. So, and as you know, the energy, the mass of all those elements is slightly less than the mass of the source U-235 atom. And so we get, after the unstable krypton and barium decay, we get about 200 MeV of energy. So a kilogram of U-235 would release about 2.6 gigawatt years of thermal energy, which would be converted to about a gigawatt year of electric power in a typical light water reactor. So that's how we get it. That's the energy density miracle, if you will, just a kilogram. Nuclear power is well known for 2 billion years. I always like this example. There was a natural nuclear power reactor in Africa 2 billion years ago. U-235 has a half-life of something like 700 million years. And so back 2 billion years ago, there was a lot more of it. Fissile U-235 was about 3% of all uranium then. Today, it's something like 0.7%. So back then, it was easier, in a sense, to put a critical reaction together. In this example, the groundwater had hydrogen and oxygen, and the hydrogen in the groundwater can absorb kinetic energy from a neutron. And so if there is a stray neutron that fissions a uranium-235 atom, the resulting neutrons can be slowed by hitting the hydrogen. And if they're slow enough, they can cause other fissions to take place. That created, again, a lot of heat and so on. The fission heat evaporated the water, the reaction stopped, and then nothing happened until more groundwater leaked in and restarted the reaction time after time in several places in Africa. People worry about fission products and so on, but they've only moved a few hundred meters in the 2 billion years since this reactor shut down. Oak Ridge, under the direction of Alvin Weinberg, who was also the instigator of the light water reactor, Oak Ridge built prototype molten salt reactors. Two. The first one was to perhaps power aircraft, and the second one was to provide power for the people. And here are the characteristics of it. What we're doing is using 50 years of nuclear science and new software, materials, and fast computers in order to do that. On the right is a picture of the so-called MSRE, or molten salt reactor experiment, which is, and you're looking at graphite rods with channels in them being assembled. The molten fuel salt will flow up through those graphite assemblies in order to allow the decaying neutrons to be slowed by collisions with the graphite, with the carbon. Thorium is a Thorcon is a thorium converter. That is to say, we can't run our reactor on thorium alone. It's possible potentially to do that, and I thought so when I wrote the book, but it's a hard project, and we're doing something simpler. We are using thorium to supplement the fuel that's largely uranium. So right in this chart, you see in the row in the middle, 235 row, is an example of uranium element 92 fissioning. But most uranium in a power plant is uranium-238, see that row up there. And it is, when it absorbs a neutron, it becomes 239, which is too heavy in neutrons. So it decays in 2 steps spontaneously to become plutonium-239, which is a fissile element, just like uranium-235 is a fissile element. So it makes power. And that's how today's power plants work. About a third or so of all the power coming out of a typical light water reactor power plant comes from the plutonium that's manufactured by neutron absorptions into U-238. Similarly, with thorium-232, if it absorbs a neutron in the lower left, it becomes thorium-233, which is a little unstable, and it decays over weeks to become uranium-233, a fissionable material. So in our case, again, about 50% of the power is going to come from 235 fission, about 25% of the power from thorium to U-233 fission, and about 25% from plutonium fission. That's that's the guts of the physics. Again, I showed you a picture of that graphite MSRE, and the right is the fully assembled unit. It was run in the 1960s. And typically, these logs are in a hexagon arrangement, hexagonal logs. We do a lot of computer simulations. A lot of code, a lot of computer programs have been developed over the years with money from governments in the United States and in Europe to put together validated models, Monte Carlo models of what happens at an atomic level, at the nuclear level, inside these kinds of power plants. So we literally track atom by atom how this is going to run, and we use, say, supercomputing capability that is available from Google and other places, which will tie together lots and lots of computers in parallel to execute the Serpent code, for example, to do these simulations where we'll simulate, what happens with 1 million neutrons. And we do that time after time as we keep changing the design. In our example, we have 3 ways inside the reactor that we can stop the fission. In this example, there's a sort of a shutdown rod. You see a kind of a Y-shaped gray area at the corners of the hexagon that is made of something like gadolinium that will absorb neutrons. And we will insert those if we wish to stop fission, if we need to. That's really a kind of a backup system. Reality is that as the temperature of the reactor increases, the fission rate slows down. We operate this reactor in a molten salt that goes up to a peak temperature of about 700 degrees centigrade. These are hot. These are a lot hotter than the temperature in a light water reactor, which is a few hundred degrees centigrade. In a light water reactor, to keep the water from boiling and keep the water solid or liquid in order to carry away the energy, there has to be high pressure, perhaps 150 atmospheres of pressure. In this kind of a reactor, we can use liquid salt, molten salt, at perhaps 4 bar pressure. But we can have a high temperature. As the temperature rises, the U-238 atoms vibrate more and more, and makes them more and more likely to interact with one of the neutrons. It will interact with a natural resonance. And so it's what's called the Doppler effect. And what it means is it slowly will stop the nuclear fission. The other thing that happens is as the salt expands, of course, the density of the material lowers and means that the reaction slows down. So we can stop fission by dropping the shutdown rod, by letting the temperature rise, or by draining the fuel cell out of the reactor into a special tank. Here's a picture of what it looks like. The thing in the middle, you're looking at the orange-like thing, is the shell of the pot. It's made of stainless steel. Inside it is the graphite moderator through which the molten salt will flow upward. Above that orange pot in the middle of the diagram, you see a blue elbow, which is the elbow of a primary heat exchanger through which the molten salt will flow. And on the upper right, you'll see a little green valve that says secondary loop. The heat exchanger moves the heat from the radioactive containing molten salt to a non-radioactive molten salt that's going to be sent to generate steam eventually. Below the pot is what's called the drain tank, in our case, 32 cylinders. The point of this is to have a lot of surface area so that we can radiate heat from the drain tank easily. In all cases, the radiated heat is absorbed by what's called the cold wall, which is that blue sleeve that surrounds the replaceable red can. So the can is a replaceable part. It contains the pot that I mentioned, the drain tanks, some makeup fuel tanks, a pump, a header tank, things of that nature, all made of stainless steel with a validated lifetime for the neutron flux that we have of over 4 years. So our plan to deal with neutron flux and corrosion and so on for all of these units is to replace them every 4 years. So the whole plant's been designed to be able to do that. The cold wall itself is a pair of cylinders with water between them, which is heated, turns partly to steam and bubbles up and creates natural circulation to a cold pond. I'll show you in a minute. Again, our point is we want to be walk-away safe. We want passive safety that's intrinsic from the physics, such as the Doppler effect I mentioned earlier that says when the reaction overheats, the fission slows down. We also have a system that any kind of break in any part here would naturally drain the fuel cell to the bottom of this can, the red can, and fall into the drain tanks. We have specifically designed it so the operator has no control over any of these safety functions. If you ever read the book called Atomic Accidents, it's kind of fun about the early work in this field by McAfee. And he points out how many accidents are caused by the operators trying to stop accidents. Our plan is that these units will be deployed by the thousands into the developing world. We don't expect to have highly trained operators that we can trust with safety functions. So this is intrinsic to the design of the unit. There's nothing the operator can do to cause a radioactive release. A little bigger picture here. I mentioned the cooling pond that has a heat exchanger in the bottom of it, a radiator, so that we recirculate cooling water to the cold wall. The cooling pond itself is open to the air, and we can cool it for months with just that cooling water if the plant is suddenly shut down without power. In addition, the vague blue color here means that there's yet another safety system that is actuated by blowout panels that will add enough water in the event of a loss of power and abandonment of the power plant to cool the plant for well over a year. Here's another diagram from our model. Set of heat transfer loops. We end up with a solar salt loop in the purple here, which transfers heat. By solar salt, I mean potassium and sodium nitrate. It's the same kind of salt that's been used in thermal solar power plants to try to store heat. We make high temperature steam, the same high temperature steam that's used for ultra supercritical coal power plants. So we can buy steam turbine generators more or less off the shelf, vastly reducing the cost of the power plant because we buy them from a competitive market that's being exploited for coal. Again, it makes electricity. People asked about earthquakes, okay? This power plant sits on sand in the water next to shore. Supposing we had an earthquake, a 1.2 G earthquake, and there was a shear transmitted to the bedrock of 1.6 G. The limit that you could transmit shear forces in waterlogged compressed sand is about 0.6 G. You just can't transmit it, just as you can't submit shear through water. And there's also a sand to hull slip limit of about 0.3 G. So we can't transmit a lot of force to the hull at all from an earthquake. The inside the hull, the can is seismically isolated. There are elastomeric bearings supporting it, and to keep it in place and not banging on the can itself, there are a series of dash pots that dampen the motion. Again, tsunamis, again, we can go up to about 15 meters of depth. So we don't want to locate the hull any place where a tsunami might be channeled into an inlet or something that would create a tsunami up to more than 15 meters. In our case, the earthquake you read about in the paper today in Indonesia is on the south side of the island. That's near the Ring of Fire. The north side, where we expect to do our power plant, is not in that zone. Why is it cheaper? Basically, it's because of energy density. The coal plant is big and expensive because all the coal it has to handle. We're talking 10,000 tons of coal every day. That's a lot of engineering, a lot of power plant to be able to do that. Dr. Gaspar Galvin raised his hand. Doctor, go ahead.
Okay. In the loop where you have the non-radioactive salt being passed heat from the radioactive salt, what material in that piping between the radioactive and the non-radioactive blocks the radioactivity of being, passed through that heat exchanger?
Stainless steel, 316 stainless.
316?
Yes. I think there's a discussion about another one, but yeah, stainless steel is adequate for that because we don't have to qualify for an 80-year life. We're qualifying it for a 4-year life at the temperatures we're working at.
Oh, okay. I guess that just kind of surprised me. How thick is it?
Oh, well, I guess I don't know the answer off the top of my head. Clearly, we want to make it as thin as we can to get the heat transfer up, but we want to balance that against the chance of a rupture.
Yeah. Okay.
Yep.
All right. Well, thank you.
Thank you. Again, I point out a rupture would not cause a radioactive release. There are 3 barriers between the radioactive fuel salt and the environment, and that heat exchanger wall is one of them. The designers who dreamed up this idea in the very first place before we founded the company have had experience. They built the largest super tankers. They use the same techniques, the same software to do the mechanical engineering design and so on. This was a $600 million plan to do, I think, 8 large tankers, which at the time were the world's largest. Okay. The power plant we're talking about is small compared to the kinds of tankers that were designed using these technologies and constructed by the South Korean shipyards. We know how to do that, and we're in communication with them. Again, the shipyards have equipment that allows partial blocks of the hull to be put together and then moved and put into place at the shipyard itself. Such a shipyard like DSME can build 20 1-gigawatt power plants a year. That would be 40 units, actually. So we could build 20 gigawatts of power in just that one shipyard. We do that math just by looking at the size, the amount of steel that's in a ship, and the amount of steel that these companies have in the past been able to produce in ships every year. So that's our mass production angle. The can has to be replaced. We need to have can fabricators. We have two vendors who are looking at becoming the can fabricators. That can, again, contains the pot, which is the vessel, the graphite moderator, the heat exchanger, the pump, and so on. We want to replace the whole unit. We have only a sketch of the can ship, but we will expect to have a reprocessing center that will reprocess the cans. Another one, may reprocess the fuel salt. Our expectation is that we're going to keep the fuel salt aboard the ship in a special place for many years until we get the world used to reprocessing fuel. Again, single shipyard, 20 gigawatts a year. I claim it's environmentally attractive. Look for a minute, replaces coal mining. Now we have to mine uranium, that's true, but it's like 100,000th of the material that has to be moved to mine uranium compared to coal. And a lot of the uranium mining today is done by injecting acid underground, more or less like fracking. Cut CO2 emissions. We do have atmospheric particulates from coal power plants that are causing deaths. Hansen and crew did a paper that showed that existing nuclear power plants saved over 1 million lives. Now, of course, the amount of particulates that are removed from the flues of the power plants depends on the local regulators. So that affects the price of the coal power plant greatly. In South America, we have, I guess not South America, and we have deforestation around South Carolina from burning wood chips that are sent to the Drax plant in the UK. Flooding of fertile land. Again, there's a lot of flooding that takes place by hydro dams in Brazil. Again, the energy supply is basically inexhaustible, particularly in a few years or a few decades when we get to fast reactors and so on. Another point not mentioned is the amount of metals and concrete used in this kind of a power plant is very small compared to that used in large windmills. And if we can make it cheaper than coal, then we don't have to subsidize the countries that want power plants. It should stand on its own economically. If we want to do the whole world, I figure it's going to be about 12,000 gigawatts to replace all the energy use in the world. We could do that if we used all the shipbuilding capacity in the world today and got all the shipbuilders up to the technologies that are possible in DSME and so on. Is it expensive? Well, I figure at this price, that's about $14 trillion. But that's not too bad, is it? Compared to what we're spending now. It's $30 per person per year. In the course that I did called Electrifying Our World, we looked at all of the various publications and came up with a really rough estimate of something like 12,000 gigawatts of power, electric power, could be converted into other uses. In the course, we talked about the use of hydrogen via electrolysis as an intermediate energy carrier. And we went through the various end uses of electricity on the far right in the magenta color and estimated the gigawatts of power needed by these various applications of energy. The whole course is done in gigawatts, average power use. You don't have to keep converting from exajoules per year and the other common nomenclature is megatons of oil So in this example, I suggested we use some biomass energy. We'll come to that. About 200 gigawatts of biomass for carbonaceous fuels for airplanes, because I think it's really hard to power airplanes with anything else. Something we didn't talk about so far is ammonia, NH3. Ammonia can be a rational energy carrier. It's got 3 hydrogens. It's used a lot today for fertilizer. It may be used as fuel in shipping in the future and potentially in heavy transport. We'll talk about those applications for a minute. In order to do that, we have to change industrial processes. Here's an example of what we use today, about 1,000 gigawatts of energy in the iron and steel industries today worldwide, 1,500 gigawatts in chemicals and petrochemicals. But if we electrify everything, we won't need nearly as much energy used in refineries and for, what's the right word, for hydrogenation of heavy fuels to make liquid transportation fuels. Cement is a big consumer of electric and actually thermal power. Aluminum, kind of rational. And the bottom here, the gigatons per year that these uses contribute. Altogether, we're pushing about 50 gigawatts, about 50 gigatons of CO2 into the air every year. Now, a lot of people are promoting biomass, and the IEA is doing this as well in their latest versions. They're proposing 4,600 gigawatts from burning biomass. But if we look at the population of the world, we need food. And if we convert food calories per year to gigawatts, we discover all of human food consumption is 900 gigawatts, plus another 400 for the animals that we're eating, and so on. So the idea of commandeering crops for energy, I think, is quite irrational. Now, we'll talk about carbonaceous fuels, though. I mentioned before that jet fuel is likely going to have to be carbonaceous because jet fuel is so energy dense. It's really great. Now, we could manufacture this stuff with hydrogen if we could find a carbon source that was more or less carbon neutral. And people say that, well, if we use crops, then we have a carbon neutral source because the carbon is going to get reabsorbed by plants anyhow. So here are typical fuels that you might fabricate if you had a source of carbon and a source of hydrogen, which we might get from electrolysis of cheap electricity. But our government has been subsidizing converting biomasses directly into ethanol, for example. So 10% of all gasoline fuel is now ethanol, and it's derived from the plants themselves. But we can use hydrogen. If we can use hydrogen instead, we can make a much more efficient conversion than looking upon the farms for generating all that energy. If we had external sources of hydrogen, we could do much better. Here's an example from a paper. If we were to burn biomass, we would get a certain, what is this example, barrels of these, this is a US example, biomass per year, 9.8 million. But instead, what we use that biomass energy to operate the biorefinery that makes the ethanol. So we lose a lot of energy in the refinery. If we were to convert our processes to make synthetic diesel using the carbon in the biomass and using external heat and external energy, we could triple the productivity that we get today from converting crops to energy. But even so, even using hydrogenation as advanced as we could, just powering the airplanes around the world today would use 5% of agricultural land today. So I think that's vaguely possible, but it's still a lot of hectares of cropland to be used to fly airplanes. But we're probably going to want to do that. Look at this chart. Petroleum and jet fuel and so on is very energy dense in terms of kilowatt hours per kilogram weight, which is important for an airplane, and also important in terms of volume, kilowatt hours per liter. Petroleum is a great fuel. Hydrogen liquid per kilogram is even more energy dense, but it's still takes a lot of room. So in an airplane, you'd have to have a large tank if you wanted to run your airplane on hydrogen. Ammonia liquid, again, not nearly as energy dense as the petroleum fuels that are used today. And part of the course I taught deals with how shipping might use it. Methane, again, a common fuel, pretty good, but uses carbon. LNG, again, a competitor. We use that to generate energy today. You can fly airplanes with LNG. Lithium-ion battery, look, it's tough. The lithium-ion battery is, look at it, 0.2 kilowatt hours per kilogram and 0.8 kilowatt hours per liter. So the energy densities that are available are much lower than the attractive jet fuel we use today. So Richard is experimenting. He flies an airplane with batteries.
We're going to need to do more zooming, I think, and cut back a little bit on flying for businesses.
Yes.
For business meetings.
Here's an airplane that did fly on hydrogen. 1988 in Russia, the Tupolev company built and flew such a plane. The hydrogen tank in the middle contains liquid hydrogen. Now, it costs a lot of money to liquefy hydrogen, of course, because you have to do that. And the problem is you can't use pressurized hydrogen because although it seems attractive, the structure of the tank to contain that high pressure means the tank would be very heavy.
Sure.
So in order to get the weight down, they had to choose liquefied hydrogen to fly the Tupolev. Yeah. And they were successful. Later on, the plane was converted to run on LNG. So Russians are way ahead. This is 1988.
Yeah.
The other thing to do to minimize the use of airplane fuel is to improve our electric train system. Why not more TGVs, as in Europe or France? Look at the chart in the lower left, the little table about the percents of rail networks that are electrified. China, 70%. India, 64%. US is only 1%. It's amazing. So, we have not invested in rail, in electrification, in high-speed rails, and that might well be a way to supplant or replace the short-haul airline flights, which are generally 800 kilometers or less. So flights, I suppose, like Chicago to New York and so on, could be accommodated with TGV type trains. In the US, of course, the biggest problem is how can you get a right of way? It takes forever. That's our problem with transmission lines. That's our problem with natural gas transmission lines, and so on. So if we could solve some of that problem, and we might be able to use more electrified transportation. All is not lost. The US Navy actually is working and has been working on capturing CO2 from seawater. There's an equilibrium balance between CO2 and seawater and the atmosphere. So removing CO2 from the ocean is tantamount to removing it from the air. The Navy is experimenting with an acidification cell in order to do reverse osmosis to get hydrogen out of the water, to get carbon dioxide out of the water, to synthesize jet fuel. And they've done it in small quantities on a plant that's the size of the skid. They would like to be able to do this to fuel jet aircraft at sea. Now they have to tanker in fuel for these fleets of jet airplanes on carriers. And yet there's a lot of nuclear power potentially available in the four engines of one of these aircraft carriers that could be dedicated to making $5 a gallon jet fuel at the time the plant's not going. So that's happening. Heather Willauer is a name you might want to look up to learn more about it. She's doing the analysis at the Naval Research Labs. And she reports that it takes about 1 kilowatt of electric power to make enough jet fuel to create 0.6 kilowatts of thermal power. She felt that isn't very cost effective, but if we could generate electricity at 3 cents a kilowatt hour, which is what Thorcon claims, that means that's about $1.67 for the electricity cost of that gallon of jet fuel. We have to add the cost of all the capital equipment and operations and so on. So it's not out of the realm of possibility at all to create jet fuel from seawater.
Could I raise a question here? If that thermal energy is manufactured by the nuclear plants in the aircraft carriers, you wouldn't have to convert it to electricity and back to thermal again.
Right. You could have a hybrid system of some sort that used some of the thermal energy as well. Right. Yes. High temperature electrolysis is an efficient or more efficient way to do hydrogen generation. Right.
Yeah. Great.
My friend Daryl Seymour likes crazy ideas. Cement is a tough issue. I mean, cement gets to what, 2,000-3,000 degrees in order to manufacture cement from sand and from what's the other quantity? Clay, I guess. The sand and calcium oxide, seashells.
Yeah.
And so his idea was that we use a plasma arc to get the temperature up. We can get only up to about 700 degrees centigrade with a molten salt reactor. If we want to get to thousands of degrees, we'd have to use something like a hydrogen arc or something or other to get the temperature up. And his idea was to use that in the heat to somehow create a cement refinery. And then he was going to also think about, wow, maybe we can take the CO2 out and put it into synfuels at the same time. So that's a dreamy idea. Maybe someone can do it someday. The best thing we can do is just do better at what we're doing. Right today, the average gigajoules thermal consumed per ton of cement is something like 5 on the lower right here. But best practice is about 2.9. So we could do better just by improving the plants that we have. Apparently there's a theoretical limit down here around 2, but it would be nice to get there. But since cement is what did I say before, 2 or 3 gigatons a year of CO2, we can improve that a lot simply by trying to get plants to get the best practice. Or have China stop building these empty cities with 33-story cement or concrete skyscrapers. That may be coming to an end. Cement has been used predominantly by China for the last decade.
Yeah.
Steel, what about steel? Steel is a big consumer of electric power. You've seen, remember the old pictures of Bessemer converters in the US 50 years ago. Steel making today uses about 900 gigawatts of thermal power and about 600 gigawatts of electric power. And we can get that electric power from nuclear. That would help a lot instead of natural gas or coal. This book, by the way, if you want to learn more, Sustainable Materials with Both Eyes Open, just Google that, you'll find it. It's available online for free now. And well, if you have engineers who want to study this, or you're just interested in the engineering, it's a lot of material in that book. It was a companion book to McKay's book, Sustainable Energy Without the Hot Air. It's a good book. What about reducing iron ore? We need to rip off the hydrogen from the ferric oxide in order to release the iron to make steel. You can do that with the current technology, and potentially you can do it with hydrogen reduction. Now, it's going to cost a lot more unless we can get the cost of hydrogen down. And in this analysis by the Hydrogen Council, they say that about $1.9 per kilogram of hydrogen, then steel production can become competitive in China. So that's the target we want. In my course, there's a chapter on hydrogen, and our friends at Lucid Catalyst and so on just recently published some papers saying that that is a viable cost, might even get as low as $1 a kilogram in the future. So you can look that up too. Rocky Mountain Institute just looks at Sweden. Sweden does a lot of iron smelting, if you will. And they're pointing out that they're looking at a demo plant that might be scaled up to do all of Sweden's 10 gigawatt use of hydrogen to create steel, iron. And that would be half of Sweden's CO2 footprint. So there's an opportunity there.
Greta Thunberg would be pleased about that.
Yes.
I watched her give TED Talks to Swedish people, and they just accept it. She gives them hell, but it's one of the cleanest countries in the world she's talking to.
Yes, right. Well, that's correct. They have a lot of nuclear power in Sweden.
Yeah.
Yeah. Nuclear and hydropower, of course.
Yeah.
We can also refine iron by electrolysis of molten salts again. Just like kind of a hybrid, right? Just the way we do electrolysis of water to get hydrogen, we can dissolve that iron oxide in molten salts, heat them up, and pass current through them, and we can do electrolysis. So you get oxygen coming off the anodes, and at the bottom of this electrolysis cell, the metal iron falls down, and we freed it up. So that's the way to convert electricity to iron, if you will. So that's a clever technology. I learned about it from Gates Notes. Bill Gates invested in this company called Boston Metals. I can't somehow show you the video I got here. I don't know why. Maybe after the session, we'll do it during the break. It's a nice video showing how Boston Metals is actually operating a little pilot lab scale plant to operate this process, which is a way to eliminate CO2 emissions and the price of electricity down. Then we can make this a competitive way to make steel, which again is a major source of CO2 emissions. Aluminum, again, if we use more aluminum, we make aluminum by electrolysis today. Some people call aluminum solid electricity because the most common, the largest ingredient in aluminum is literally electricity. That's the biggest cost to make aluminum. And others are thinking out wide. We're thinking of building electric power plants in shipyards, but others are thinking of building other kinds of factories in shipyards. If we're going to have to convert the energy system of the world, we're going to create more factories. Here's an example of a factory, the Prelude. It is a factory that liquefies natural gas. And it's stationed off Australia, larger than 5 aircraft carriers. They are stationing it over a natural gas field. And when that gas field is depleted, they will move that liquefying plant to some other place. But that same technology can be used for example, hydrogen electrolysis plants, or perhaps even steel electrolysis plants. So it's a way to think of other ways to meet our goals. I've been working on a couple of things, and one is I got a new book out. It came out the same time as Bill, oh, I can't show it. Oh, well, it came out at the same time as Bill Gates's book a couple of months ago. Bill Gates, you know, wrote a good book. It's very readable for the common public, I think, about technologies that we ought to invest in to avoid a climate disaster. Gates himself is a founder and investor in TerraPower, which is a kind of an electric power generated company or research company, really, that uses liquid sodium reactors that use unmoderated neutrons that can actually consume U-238 as fuel. And they're lately coupling it with molten salt storage to allow better load following.
Could I ask you what you think of that approach compared to what you're able to do with molten salt reactors? In this case here, it's, as I understand it, called natrium, and they're trying to integrate solar and wind with nuclear power. What do you think of that? Is it possible that Bill will have easier approval by NRC because they're the NRC might be prejudiced against molten salt reactors, but not prejudiced against molten salt storage? Any thoughts on that?
I honestly don't know. I honestly don't know. Bill Gates and that company originally were developing that sodium cooled fast reactor in the US. They got into so much red tape with the NRC, they moved the operation to China to do it there. And then about a little over 2 years ago, Trump suddenly made that impossible because we're not allowed to share any such technology with China.
Right.
So all that investment was scotched, more or less. His company is, we kind of think of it more like a national lab. They're not so much planning to make a profit building power plants, but they're trying to further the technology and make it available and license it, I suspect. Now, they just recently added the idea of the molten salt storage. We've toyed with the same idea because our last loop is a molten salt loop. We could expand that to have more volume so that we could, in fact, what can I say? We could, in fact, store more energy and do a better job at load following. Our objective is to do what we can with the technologies that exist now. So we didn't do fast reactors. We did the technologies that were proven at Oak Ridge. We're using the molten salt the fluoride salts that Oak Ridge dealt with, although chloride salts might work in a molten salt fast reactor, maybe.
So are your neutron energies pretty much thermal as opposed to liquid sodium reactors? They're much, because of all the graphite, you bring down the energy, neutron energy a lot?
Yeah, that's correct. We are fully thermalized, very close to fully thermalized. It makes it easier to control a reactor. If you have a reactor that's not fully thermalized and it's critical, you run the risk of getting a moderator near something, water or carbon or whatever, and speeding up the reaction out of control. So it's much simpler to run a moderated reactor. The safety case is a lot easier.
And you can still, what about recycling the fuel? Is it the way you're doing it with these 4-year replacements? Are you able to consume most of the fuel with a closed cycle of thorium? Is it as efficient as the sodium reactors out in Idaho?
No, we are able to be a little more efficient than the common light water reactors, but in order to make room for new fuel, we remove old fuel, and the fuel that we take out of the power plant is very valuable and has a lot of uranium still in it. We intend on storing that fuel in the power plant for an indefinite period. We have enough storage for the 80-year life of the power plant. But the most efficient and economic thing to do with it is to be allowed to refine it and take out the valuable uranium and plutonium and so on. But we don't want to overcome that hurdle at this time. We want to be able to be in operation as soon as possible using the technologies and the commonly accepted rules that govern the transport of fuel in the world.
Thank you so much for answering my questions. I'm feeling a little guilty. It's 11:35. You probably have a few more slides, and I want others to
No, this is good.
Questions.
This is good. At the bottom of this slide, you'll see electrifyingourworld.com.
Yes.
That's where all the slides are from this course that I gave. And almost all the slides you saw today are there. So if you go to that course site, you can find them, and you can even find, and I put that together to make this new book, Electrifying Our World, which is available on Kindle and also in hard copy.
Thank you. I've already done that a little bit. I've even stolen a couple of slides which I figured you wouldn't mind, for using to a different Plato group that we have here, where they want to get some real basic introductions. And your slides are wonderful at that site. I really appreciate them a great deal.
Good.
Okay, we have a couple of questions here. If I can read them out to you. The first one is from Mert Corwin. He says, if the US regulatory agencies approved the Thorcon plans, are there US companies that are capable of and interested in manufacturing these reactor systems? That's a great question, Mert. Go for it.
You know, that's a problem. Potentially, yeah, but as a practical matter, no. For example, we talked about competition in shipping, and the reason we picked the South Korean shipyards is because they are highly efficient, highly competitive. The ones in the US are not. We passed the Jones Act years ago, which says that you cannot transport any materials between US ports except in ships that were built in the US and use US crews. So we thought somehow or other that was going to create an incentive. But the reality is the shipping business in the United States is not competitive. The shipyard building is not. So yeah, potentially, but not at the price we need.
Yeah, it's a sad situation that China and Russia are getting all the action with a process that we invented, and it's really needs to be corrected. I don't know if Biden can do that with some of his plans or not, but it's a serious problem.
The most expensive part of the power plant is the steam turbine generator.
Yeah.
Okay, now GE can manufacture those. Siemens can manufacture those. Daewoo Heavy Industries and so on. These are international companies. GE bought a company in France, I've forgotten the name of it, in order to do that. But we look upon the supply chain as being international.
Yeah.
Yeah.
I think they bought EDF, maybe.
Yes, maybe.
Yeah.
Well, I don't know.
Not sure either. But this is another question. That's a good question, Mert, and a depressing but important answer. Alan Pentikoff has a question, two of them, two short ones. He asks, first, how small can a Thorcon power plant be made? And his second question is, what are the prospects for direct heat to electricity conversion without steam?
Okay, let me do one or the other.
Yeah.
How small could you make it?
Yeah.
I guess I'm not sure. I suppose the MSRE was a small one. The one that was done at Oak Ridge, it was on the order of 10, 20 megawatts thermal. I've forgotten the real number, but something like that.
Okay.
So you could build a small one. Yes. The size of the plant that we manufacture is guided by our objectives. Our objectives are mass production, which means shipyards, which means the width of the plant is 65 meters. Okay. So in that 65 meters, we can put 2 reactors, and that's where they are. We want to optimize the cost of this conversion of heat to electricity, and that scales with the steam turbine size. So we use 2 thermal power plants that generate 557 megawatts thermal to jointly power 1 steam turbine that will eventually generate 500 megawatts electrical. So that's how the size of the plant comes to be. It's not because we want it to be a small modular reactor. It's because we wanted to manufacture them in shipyards. So we're not aiming at the small power plants. They're going to be more expensive per kilowatt hour to do that. We conceivably could do a 1 module plant instead of a 2 module plant. But again, unless we can get the price below the price of coal, we're not going to be successful at the business or the long-term objective, which is to basically replace the thermal energy industry with this kind of a power source.
Okay. The second question was, what are the prospects for direct heat to electricity conversion without steam?
Well, I don't know how to do that. I have no idea. I guess some of the new fusion power plants are looking at that sort of idea. I don't know how to do that.
Okay. Good.
Maybe Dr. Gasper Calvin knows.
Dr. Bulent Atelier. Bulent, do you want to have a crack at that? Let's see. So far, I've got while we're waiting for other questions, I've got a quickie about Dr. Lars Jorgensen. He is your CEO, I believe.
Yes.
And I'd just like your thoughts on how you interact with him. Are you, is he the perfect CEO? It's perhaps a touchy question to ask you to speak publicly, but whatever you'd like to share with us about the functioning of the company and where you're planning on going after Indonesia. You have a lot more plants to build down there. Are you thinking about India or China? What's the long range plan?
Yeah. Lars is a Stanford grad. He's got, I think, two master's degrees of electrical engineering and something else. And he lives in California. Mm-hmm. Our whole company is spread over the world. We meet via, not Zoom, but we meet by Teams from Microsoft. We met by Google, on and on.
Sure.
we communicate by email and phone and so on.
Yeah.
So that's how the plan, the whole
Are
system.
you happy with how it's moving along?
Sure. And the
As a
whole world
co-founder,
is now that COVID has put everyone in this position. So it works out well for us. We have a lot of the neutronics done by Milano Multiphysics, which is a small consulting firm in Milan. We have another consulting firm in Sweden. We have another one in Korea. Yeah, we're spread over the world, and we're happy enough doing it this way. Right now, we're trying to integrate everything on the Microsoft 365 platform.
and this is as far as you're thinking at the moment is Indonesia, but there's lots of room to grow, not only around Indonesia but to other countries, right?
Sure. Sort of informally, we have an agreement with Indonesia to do a total of 3 gigawatts of these kind of power plants, obviously depending upon the first one being successful. But so once the first one is successful, we must follow that agreement and provide the next ones to Indonesia as well. Obviously, if it catches on, there are going to be a lot of people who are going to want licenses or want to try to emulate what we're doing and so on. So once we have energy cheaper than coal from power plants that can be created in less than a year, we expect 2 years from order to grid connection, then the sky's the limit. There's got to be a lot of people wanting to do this. So we're not worried about what the next is. But, you'd be surprised. India, for example, I mentioned earlier, is building a lot more coal plants. I think Rosatom is successful there. The US has not been successful there. One of the problems in dealing with India is they want unlimited liability on the suppliers.
Yeah. What about your rough estimate on when you think the first reactor might be powering the grid in Indonesia? What would be your guesstimate? 5 years, 10 years?
Well, let's see. Our plan is we got about a year to complete some more engineering this year. And next year, we will begin construction of what we call the pre-fission prototype. We'll do that somewhere in Indonesia. It has all of the functionality of the pumps and the heat exchangers and the vessels, the pots, the graphite, and so on, but will not use fuel that's got enough energy, got enough uranium in it to be fissionable. We're going to just use natural uranium so that we can just check everything out and in an environment where we don't have to worry about remote handling and radiation. The engineers can look at anything they want and so on. So that'll take 2 years, starting in 2022. So at the end of that 2-year period, we'll begin construction. That'll be 2024 of the plant in a shipyard in South Korea. And in 2025, have it delivered to Indonesia. There we expect to be in operation in test mode for a couple of years. And in the second year, delivering substantial energy to the grid.
So a total of, I think, if I wasn't doing the math, you're talking 5 to 10 years then before.
Or 5 years, yeah.
Yeah, okay,
Yeah.
Excellent. Dr. Bulent Attalay is making comment to the panelists, and you in particular. He said this was a superb lecture, illuminating and thorough. Thank you. He has a question. He asks, in liquid sodium circulating reactors, he believes that the refrigeration system patented by Einstein and Szilard around 1927 was evidently used. Is there any similarity in the circulation systems in the liquid sodium and the Thorcon reactors?
I guess I don't know the details of that. We do have an off-gas system that requires a lot of refrigeration. We separate the xenon and krypton from the helium cover gas, but that's the only refrigeration that I know of. Well, then there's an additional refrigeration system that we use for the valve. At the bottom of the vessel circulating loop, there is a freeze valve that's kept cold with refrigerated helium, but that's
Yes.
it.
Yeah. Okay.
Somebody was asking earlier, this is Lee Gasper Galvin, was asking earlier if you can make electricity directly without steam. And basically to make electrical power, you need to expand some kind of medium, such as steam or expanding combustion gases into the turbine blades to spin them. So, that's how you make the electric power, is that you're spinning turbine blades, which then spin magnets with, coils of metal, which, produces your electricity, right? So you cannot go directly from the nuclear power without steam, to make the electricity.
Well, as I understand, there are some reactors, not reactors, accumulations of plutonium decaying on Mars today that are generating electricity from heat. I presume that's a photoelectric effect of some, maybe not a photoelectric, some thermoelectric kind of conversion. Any comments on that, Robert?
Sure. Anytime you have a heat source, as in a space vehicle, you have hot something like plutonium or strontium or something or other, and you can convert that. If you have a radiator, just a bunch of fins that are going to radiate to outer space, you connect the two of them together, and you can use a number of conversion technologies in the middle, heat pipes, whatnot. I'm not an expert in thermodynamics. There's also an electronic system that you can use. What do you call it? The piezoelectric effect? Is that it?
Yeah.
Yeah.
Right.
I don't know that you could do it for large power.
Yeah, that would be pretty small, but presumably that's what they're doing on Mars. They don't use a lot of electricity there.
There's NASA has a new one. It's a kilowatt power. So it's not piezoelectric effect, but they're planning to send it off.
Okay. Any
I
other
have a
questions
question.
there?
I was wondering, I've heard a lot about the idea of using residential natural gas lines to transport hydrogen. Now, my concern about that would be that you might have a hydrogen embrittlement problem. Also, hydrogen's much smaller than natural gas, so you might have more leaks and that kind of thing. So what are your thoughts about that?
Well, my thoughts are that, of course, the hydrogen is going to be more expensive than the natural gas. So there's not a lot of incentive to do that.
What about nitrogen?
The things I've seen have only had a mixture. I've seen proposals for perhaps 10% of the natural gas being hydrogen.
Then wouldn't your hydrogen float up to the top of the pipe and separate because it's a lot less dense than natural gas? That didn't make sense. I heard that too. And it just didn't make sense to me that would work like they kind of were proposing it would.
I do not know. It doesn't make sense to me to take heat, make it into electricity, make it into hydrogen, and then burn it to get heat. It just seems like
right.
Right.
The theory I've heard is that you could put compressed air or nitrogen, which is 80% of our air, into the gas lines, and have every house fitted with a small air pump or nitrogen pump, and just use that to make electricity in each home. We have compressed air pumps in French automobiles that drive cars and recharge batteries. So you could have theoretically nuclear reactors in putting air or nitrogen into gas lines, maintaining a pressure at sufficient level to drive little air pumps in each house that would then generate electricity for that house.
Yeah, we've also had compressed air energy storage in the US, where you compress the air, stick it in a cavern somewhere, and then when you want to generate more electricity, you use the pressure from that compressed air to drive a turbine to make the generator run. Problem with it, of course, is when you compress the air, it heats up and you lose heat through the walls of the cavern and so on.
Yeah.
So the ones that I've seen, you need natural gas to heat up the air as well when you recover the energy that's left in the cooled, compressed air.
Yeah.
But you do remind me of a great slide I got ahead. Let me find.
Oh, yeah.
Let me find it. Hold on a second. This one, California. This is crazy. They're nuts out there. They're passing laws in California now, Boston, and on. It says, well, we won't allow any new gas stoves. We're not going to allow gas hookups. And even the New York Times says, oh my, we're going to convert away from gas stoves and save the planet. But let's look for a minute at the math here. In a stovetop burner on the top left here, if you have a 2 kilowatt burner, which is about what they are, and you run electricity for it and it gets hot, it makes about 2 kilowatts of thermal energy. The media doesn't understand the difference between useful electric energy or gravitational potential energy and so on, and heat or thermal energy. So again, 2 kilowatts electric makes 2 kilowatts thermal. Now to get that 2 kilowatts, I'm saying, well, the California utilities burn natural gas. That's the largest source of electricity in California.
Yeah.
And it takes about 3 kilowatts thermal to get 2 kilowatts of electricity, a little less maybe. So the electric utility burns 6 kilowatts of thermal, but the customer could have burned 2 kilowatts of natural gas on his gas stove. So by taking out his gas stove, we almost triple the amount of natural gas that's burned. Now people are going to say, oh, they're not going to burn the natural gas. They're going to say, oh, it's going to come from the windmills. It's going to come from the solar panels. But of course, when people turn on their gas stoves, the sun is set. And when they turn on their gas stove, the wind isn't going to blow any stronger. Somewhere in the system, a little gas valve is going to open up to provide a little more electricity that way. On the New York Times side, they're saying the same thing. They haven't done the analysis. The reporters are not educated enough to realize the problem. They're focusing instead on, oh, and while we're at it, we better have induction electric stoves, because if we just heat the metal pots with an inductive coil, then we don't waste the electricity that heats the air that goes up alongside the pot and doesn't get into the food. DOE did some analysis, and it's slightly more efficient to have an induction gas stove than a coiled one on the left, but not 10% better. So meanwhile, everyone's doing the same thing. They're saying, okay, we're going to ban gas hookups. I don't know.
Crazy. Well, that is great. I think that you've brought some great slides along for our discussion, and wonderful collection of slides in your talk. I'm glad this is being recorded, and look forward to passing that along to you and to anyone else who would like to get them. They're on the website for platomadison.org. And there's a section there for recorded talk, so that will be available. And thank you very much, Dr. Robert Hargraves. It's a delight to have you join us and speak to us in such an engaging manner.
Thank you very much.
Bye-bye now.
Bye.
Bye-bye all.